Tonight, we're going to take a gentle walk through something that feels both familiar and impossibly distant. The home galaxy we've been orbiting inside since before humans ever looked up and wondered what those soft white smudges in the night sky might be. The Milky Way. A name that sounds almost cozy, like something you might pour into a glass before bed, but in reality it's a structure so vast that even our best maps still struggle to capture its full shape. And recently, a new set of eyes has begun quietly peering into its deeper corners, not with a dramatic fanfare or a cosmic drumroll, but with patient, careful observation. The James Webb Space Telescope has been sending back information that gently suggests something surprising. The Milky Way might be larger, deeper, and more complex than we've been telling ourselves for a very long time. Before we drift too far into that thought, let me ask you something simple and human. Where are you listening from right now? A bedroom? A couch? A quiet train ride? Or maybe a place where the lights are already dim and the world has begun to soften at the edges? And what time is it for you in this moment? In your own small corner of a galaxy that stretches hundreds of thousands of light years in every direction. If you find this space relaxing, or if you enjoy letting your thoughts wander slowly among stars and ideas, you're always welcome to like the video or subscribe. It helps this calm little corner reach others who might be looking for a gentle way to end their day. But for now, there's nowhere else you need to be. The universe is not in a hurry, and neither are we. So let's begin with something that seems simple on the surface. The Milky Way is our galaxy. That's the sentence most of us learned in school, written on a chalkboard or printed in a textbook beside a spiral diagram with a bright dot labelled, "You are here." It feels tidy, it feels manageable, a disk of stars, some arms curving outward, a glowing centre, and our solar system sitting politely off to one side like a guest who arrived early and isn't quite sure where to stand. But even that familiar picture hides a quiet problem. No one has ever taken a photograph of the Milky Way from the outside. Every image you've seen of our galaxy as a whole is an artist's interpretation, a careful guess based on years of measurements, motion tracking, and light analysis. We live inside the thing we're trying to map. It's a bit like trying to draw a forest while standing in the middle of it, surrounded by trees, mist, and shadows. For most of human history, the Milky Way was not even a galaxy. It was a pale, milky band across the night sky, something to build stories around. Ancient cultures saw it as a river, a path for spirits, a trail left by gods, or spilled light from some cosmic event long forgotten. It wasn't until the early 20th century that astronomers realized that this soft stripe of light was actually made up of billions of stars, and that our sun was just one among them. Even then, understanding its true size was a slow and careful process. Early astronomers tried to measure distances by observing how stars appeared to shift position as Earth moved around the sun. This method, called parallax, works beautifully for nearby stars, but as soon as you start looking deeper into the galaxy, those shifts become so tiny that they're nearly impossible to detect. The Milky Way, it turned out, was playing a very effective game of hide and seek. To make things even more complicated, our galaxy is filled with dust. Not the kind that settles on shelves, but fine and cosmic grains made of carbon, ice and silicates, drifting between stars. This dust absorbs and scatters visible light, creating dark patches and glowing clouds that block our view of what lies beyond. If you've ever tried to look through a foggy window at night, you have a good sense of what astronomers have been dealing with for decades. So for a long time, our maps of the Milky Way were built from what we could see directly, combined with what we could infer. We tracked how stars moved. We measured how gas clouds glowed in radio waves. We watched how clusters of stars formed and drifted. Piece by piece, a picture began to emerge. A spiral galaxy about 100,000 light-years across, with several major arms, a central bulge, and a vast halo of faint stars surrounding it, like a quiet, invisible ocean. That model worked well. It explained the motion of stars. It fit the data we had. It gave us a sense of scale that was already so large it was hard to truly feel. 100,000 light-years means that light, moving at the fastest speed anything can go, would take 100,000 years just to cross from one side of the galaxy to the other. Every time you blink, light could have travelled around the Earth 7 times, and yet in galactic terms that's barely a step. Then, Quietly, without much ceremony, James Webb opened its eye. The James Webb Space Telescope is not a traditional telescope in the way people often imagine one. It doesn't sit in a dome on a mountaintop. It doesn't point a glass lens at the sky and collect visible light. Instead, it floats far from Earth, nearly 1 million miles away, at a point in space where the gravitational pull of Earth and the Sun balance just enough to let it hover in a stable position. From there, it looks outward and inward, not with human eyes, but with instruments tuned to infrared light. Infrared is the kind of light we feel as heat. It's what lets you see warm shapes in a thermal camera. And in space, it has a special advantage. Infrared light can pass through dust clouds that block visible light. Where traditional telescopes see darkness, Webb sees structure. Where older instruments see a blank patch of sky, Webb sees stars being born, galaxies forming, and distant objects glowing faintly in the background. When Webb began observing regions of the Milky Way, astronomers weren't expecting a dramatic rewrite of the galaxy's size. They were looking for details: star formation, the chemistry of nebulae, the structure of the galactic center. But as data accumulated, patterns started to appear that didn't quite fit the neat, familiar model. In some directions, Webb detected stars much farther out than expected. Not just a few scattered stragglers, but extended populations of faint, distant stars that suggested the galaxy's disk and halo might stretch farther into space than previous measurements indicated. These weren't bright, obvious objects. They were subtle, quiet points of light, the kind that only show up when you look with patience and the right kind of vision. One of the challenges in measuring a galaxy's size is deciding where it actually ends. There's no clear edge, no galactic fence marking the boundary between Milky Way and not Milky Way. Instead, the density of stars slowly thins out. The bright spiral arms fade into scattered clusters. The disk blends into a halo of old, dim stars that orbit far from the center. Beyond that, there's intergalactic space, where the distances between stars grow so large that the concept of a galaxy starts to feel more like a suggestion than a solid shape. Webb's ability to detect extremely faint infrared signals has made it possible to see parts of this halo in greater detail than ever before. And what it's revealing is that the Milky Way's influence, its gravitational reach, and its population of stars extends farther than we used to think. To understand why this matters, it helps to imagine the galaxy not as a flat picture, but as a three-dimensional structure. There's the thin disk where most of the stars, gas, and dust live. That's where the spiral arms are, where new stars form, and where our solar system happens to be. Then there's the thick disk, a puffier, older layer of stars that sits above and below the thin one. And surrounding all of that is the halo, a vast, roughly spherical region filled with ancient stars and dark matter. Dark matter is another quiet player in this story. It doesn't emit light. It doesn't absorb light. We can't see it directly at all, but we can see its effects. Stars in the outer parts of the galaxy move faster than they should if only visible matter were present. Something else is adding extra gravity, holding the galaxy together like an invisible framework. That something is dark matter, and it likely makes up most of the galaxy's mass. When Webb observes the outer regions of the Milky Way, it's not just looking at stars, it's helping astronomers trace the shape of this hidden structure. The farther out stars are found to orbit in stable patterns, the more we learn about how far the galaxy's gravitational influence truly extends. In some recent studies, astronomers using Webb's data alongside other observatories have suggested that the Milky Way's stellar halo could stretch hundreds of thousands of light years from the center. That doesn't mean it's packed with stars all the way out there. It means that the galaxy's presence, its faint, quiet population of ancient stars, and its dark matter envelope reaches much farther into space than the bright, familiar spiral arms. It's a bit like realizing that the cozy, well-lit rooms of a house are surrounded by a sprawling, dimly lit yard that you never noticed before. The house is still the part where most of the activity happens, but the property line is much farther out than you assumed. There's another layer to this story, and it comes from looking not just at where stars are, but how they move. The Milky Way is not alone in space. It's surrounded by dozens of smaller satellite galaxies, like the Large and Small Magellanic Clouds, along with many faint dwarf galaxies that are so dim they're hard to detect at all. These smaller systems orbit the Milky Way, drawn in by its gravity, sometimes being stretched and torn apart in the process. Webb's observations of stars in the outskirts of the galaxy have helped astronomers identify streams of stars that don't quite fit the main rotation of the Milky Way. These streams are the remains of smaller galaxies that wandered too close and were gradually pulled apart, their stars now forming long, faint trails that wrap around our galaxy like cosmic ribbons. The presence of these streams tells us that the Milky Way has grown over time by absorbing other galaxies. It's not a static object. It's a structure built through countless slow encounters, mergers and gravitational dances that have been playing out for billions of years. And this growth process contributes to the galaxy's true scale. The more material it has absorbed, the farther its halo extends. The more dark matter it gathers, the larger its gravitational footprint becomes. Webb's ability to see faint, distant stars makes these ancient interactions easier to trace, revealing a history that is written not in words, but in motion and light. Now, it's worth pausing for a moment to think about where we are in all of this. Our solar system sits about 26,000 light-years from the center of the galaxy. That's far enough out that we're not in the crowded, energetic core, but still well within the bright, active disk. We orbit the center once every 230 million years or so. That means that since the first dinosaurs appeared on Earth, the Sun has gone around the galaxy just once. From our position, we look out through layers of stars, gas, and dust in almost every direction. The night sky we see is shaped by this placement. We see the Milky Way as a band because we're looking along the plane of the disk, where stars are most densely packed. When we look up or down, away from that plane, the sky becomes darker and emptier because we're looking out of the disk and into the halo. Webb's discoveries gently remind us that even in those darker directions, the galaxy doesn't simply stop. It fades, it stretches, it becomes quieter, but it continues. This idea of a galaxy without a sharp edge can feel a little unsettling. We like boundaries. We like knowing where things begin and end. But the universe doesn't always cooperate with that preference. Structures in space often blur into one another. Galaxies interact. Halos overlap. Gravity weaves everything into a kind of slow, continuous network. In a way, learning that the Milky Way is larger than we thought doesn't make it more distant. It makes it more present. It means that the space around us, the region we move through every second as Earth spins and orbits the Sun, is part of a much bigger system than the neat diagram suggested. We're not just inside a disk of stars. We're inside a vast, layered structure that reaches far into the dark between galaxies. And this is only part of what Webb is beginning to show. Its observations are still accumulating. New data sets are being analyzed. Patterns are being checked and rechecked. Science moves slowly here, not because it's uncertain, but because it's careful. Each claim about the galaxy's size and structure has to be supported by multiple lines of evidence from different instruments and methods. As that work continues, our picture of the Milky Way will keep shifting, not in sudden leaps, but in small, steady adjustments. A little farther here, a little more mass there. A faint stream of stars added to the map. A new region of the halo traced in more detail. If you let that idea settle for a moment, it has a gentle kind of effect. The galaxy is not a fixed backdrop. It's an evolving environment. It's something we're moving through, something that's changing around us on timescales far longer than a human life, but not so long that they're meaningless. And as we follow this trail of thought, it naturally leads to another question that doesn't rush for an answer. If the Milky Way is larger than we believed, if its structure is more layered and extended, then what does that mean for how we understand our place within it, and how we compare our home galaxy to the countless others scattered across the universe? For a long time, the Milky Way felt like something we had more or less figured out, not in the sense that every star had been counted or every cloud of gas neatly catalogued, but in the comfortable way you might feel about a familiar neighborhood. You know the main roads, you recognize the landmarks, you have a general sense of where things are, even if you've never explored every side street. That was the relationship astronomers had with our galaxy for much of the last century. There was a working model, a shared mental map, and a quiet confidence that while details would change, the overall shape and scale were reasonably well understood. If you open a textbook from just a couple of decades ago, you'll likely find a familiar picture. The Milky Way is drawn as a barred spiral galaxy, a flat disk of stars with several curved arms wrapping around a bright central bulge. Our Sun is placed somewhere between two of those arms, about halfway out from the centre, marked with a small, humble dot. Around the disk is a faint spherical halo of old stars and globular clusters, and beyond that, a vast invisible envelope of dark matter that holds everything together. It's a clean image. It fits nicely on a page. It's easy to remember. And for a long time, it worked well enough. The roots of this picture go back to a period when astronomers were just beginning to realize the true scale of the universe. In the early 1900s, there was still debate about whether the Milky Way was the entire universe or just one island of stars among many. Some thought that the faint, fuzzy spirals seen through telescopes were clouds of gas within our own galaxy. Others suspected they were separate galaxies far beyond it. That question was settled in 1924, when Edwin Hubble measured the distance to the Andromeda Nebula and showed that it lay far outside the Milky Way. Suddenly, our galaxy went from being the whole universe to being one among billions. But even with that revelation, understanding the Milky Way itself remained a challenge, because we were still stuck inside it, trying to measure it from within. One of the first big steps toward mapping our galaxy came from studying star clusters. Globular clusters, in particular, turned out to be useful guides. These are dense, spherical collections of very old stars that orbit the center of the galaxy, mostly in the halo. By measuring their distances and plotting their positions, astronomers noticed that they weren't evenly distributed around the Sun. Instead, they seemed to cluster around a point far away in the direction of the constellation Sagittarius. That point, it turned out, marked the true center of the Milky Way. This discovery, made in the 1990s by Harlow Shapley, shifted our sense of place in a profound way. We were no longer near the center of the galaxy. We were off to the side, one star system among many, orbiting a distant, crowded core. The Milky Way became something larger, more structured, and less centered on us. As telescopes improved, astronomers began to identify the spiral arms of the galaxy by tracing regions of star formation. Young, massive stars shine brightly and don't live very long, so they tend to stay close to the gas clouds where they were born. By mapping these bright stars and the glowing hydrogen gas around them, scientists could sketch out the rough pattern of the Milky Way's arms. Over time, a consensus emerged. The galaxy appeared to have 4 major spiral arms, along with a few smaller spurs. The disk was about 100,000 light-years across. The central bulge was thick with stars, and a long bar of stars stretched across the center, helping to funnel gas inward and fuel new star formation. This model was supported by observations across different wavelengths. Radio telescopes mapped clouds of hydrogen gas. Infrared telescopes peered through dust to see stars near the galactic center. Optical telescopes filled in the nearby regions with detailed star catalogues. Each piece of the electromagnetic spectrum added another layer to the picture, like stacking transparent maps on top of one another. And yet, even as this image solidified, there was always an awareness that it was incomplete. One of the biggest limitations was distance measurement. Knowing how far away something is in space is surprisingly difficult. For nearby stars, astronomers use parallax, the apparent shift in a star's position as Earth moves around the Sun. This method is precise, but it only works reliably out to a few thousand light-years. Beyond that, the shifts become too small to detect with traditional instruments. For more distant stars, astronomers rely on standard candles, objects whose intrinsic brightness is known. By comparing how bright they appear to how bright they should be, you can calculate their distance. Certain types of variable stars, like Cepheid variables, are especially useful for this purpose. They pulse in brightness in a way that's directly related to how luminous they are. But even these methods come with uncertainties. Dust can dim light. Crowded regions can make stars blend together. Different types of stars can be mistaken for one another. Each measurement carries a margin of error, and when you stack thousands or millions of these measurements together, those small uncertainties can add up. So the Milky Way we thought we knew was always a bit fuzzy around the edges. Another challenge came from the fact that the galaxy is not static. Stars move, gas flows, spiral arms shift and change over time. The Milky Way is not a frozen snapshot. It's more like a slow-motion scene, where everything is drifting, orbiting, and evolving on timescales that stretch far beyond a human lifetime. This dynamic nature means that any map of the galaxy is a momentary approximation. It captures where things are now, not where they were millions of years ago, or where they'll be millions of years from now. And because light takes time to travel, even now is a relative term. When we look at a star 10,000 light-years away, we're seeing it as it was 10,000 years in the past. So in a very real sense, our picture of the Milky Way has always been a patchwork of different eras stitched together into a single image. Despite these complications, the basic structure seemed solid. The disk, the arms, the bulge, the halo. These elements appeared again and again in observations and models. Astronomers could simulate how such a galaxy would form and evolve, and the results matched what we saw in the sky. There was comfort in that consistency. It suggested that we had a handle on the big picture, even if the details were still being filled in. One of the most powerful tools in building this picture was the study of stellar motion. By measuring how stars move through space, astronomers can infer the gravitational forces acting on them. This, in turn, reveals how a mass is distributed throughout the galaxy. When these measurements were first made, they led to a surprising conclusion. Stars in the outer parts of the Milky Way were moving faster than expected. According to Newton's laws, if most of the galaxy's mass were concentrated in the visible stars and gas, then stars farther out should orbit more slowly. But they didn't. The only way to explain this was to assume that there was a large amount of unseen mass extending far beyond the visible disk. This was one of the key pieces of evidence for dark matter. It suggested that the Milky Way is embedded in a massive invisible halo that dominates its overall mass and shapes its motion. This realization expanded the galaxy in a conceptual sense, even if the visible stars still seem confined to a relatively neat disk. The true Milky Way, it turned out, was not just what we could see. It was also what we could feel through gravity. As surveys grew more comprehensive, astronomers began to discover faint dwarf galaxies orbiting the Milky Way. Some were found because they contained small numbers of stars that stood out against the background. Others were detected through subtle patterns in star motion. Each new satellite galaxy added another layer to our understanding of the Milky Way's environment. These small companions were not just decorative, they were evidence of the galaxy's history. The Milky Way, like many large galaxies, has grown by absorbing smaller ones. Over billions of years, it has pulled in and torn apart dwarf galaxies, scattering their stars into long streams that now arc through the halo. By mapping these streams, astronomers could reconstruct parts of the galaxy's past, identifying where and when it had interacted with other systems. This process revealed the Milky Way as something more like a collector than a solitary island, shaped by a series of slow, gravitational encounters. Even with all this, the general scale of the galaxy seemed settled. About 100,000 light-years across for the disk, a halo extending perhaps twice that. A total mass dominated by dark matter, roughly 1 trillion times the mass of the Sun. These numbers appeared in papers, lectures, and public science books. They became part of the shared language of astronomy. If you asked someone how big the Milky Way was, you'd likely get an answer in that range. But those figures were always based on the best available data at the time. And science, by its nature, is provisional. It builds models that work until new evidence suggests they need revision. One area where uncertainty lingered was the outer regions of the galaxy. The halo, in particular, is faint and difficult to study. Its stars are old and dim. They're spread thinly across vast volumes of space. Detecting them requires sensitive instruments and careful analysis to separate them from background objects in distant galaxies. For a long time, most surveys focused on the brighter, denser parts of the galaxy. The disk and the nearby halo were relatively well mapped. The far halo remained largely unexplored, a region where data points were sparse and interpretations tentative. This meant that our sense of where the Milky Way ended was partly a matter of convenience. We defined boundaries based on where our observations dropped off, not necessarily where the galaxy itself truly faded into the cosmic background. There was also the issue of perspective. Because we are inside the disk, our view is heavily biased. We see the galaxy edge on when we look along the plane, and face on only in small patches when we look up or down. This makes it difficult to get a global sense of shape and extent. Astronomers have developed clever methods to compensate for this, using star counts, motion data, and models of galactic structure. But no method is perfect. Each relies on assumptions, and those assumptions can subtly influence the results. For example, when estimating the total number of stars in the Milky Way, scientists have to extrapolate from the regions they can see to the regions they can't. If the density of stars in the far halo is higher or lower than expected, the total count changes. The same goes for mass estimates based on how fast stars and gas are moving at large distances from the centre. These uncertainties don't mean the old model was wrong, they mean it was a best guess based on incomplete information. Another piece of the puzzle came from comparing the Milky Way to other galaxies. Astronomers observed spiral galaxies of similar size and brightness in the local universe, and used them as points of reference. If those galaxies had certain properties, it was reasonable to assume the Milky Way might be similar. This comparative approach helped fill in gaps, but it also introduced its own assumptions. Our galaxy could be typical, or it could be somewhat unusual. Without an external view, it's hard to be sure. Over time, more advanced surveys began to chip away at these uncertainties. Space missions like Gaia started measuring the positions and motions of over 1 billion stars with unprecedented precision. This created a detailed three-dimensional map of the nearby galaxy, revealing streams, clusters, and subtle structures that had never been seen before. Gaia showed that the Milky Way's disk is not perfectly flat. It's warped and rippled, like a vinyl record that's been left in the sun too long. It revealed that the galaxy has experienced recent interactions with satellite galaxies, leaving waves of motion that are still propagating through the stars. These findings added texture and complexity to the picture. The Milky Way was no longer just a neat spiral. It was a dynamic, slightly messy system, shaped by ongoing gravitational relationships. And still, the question of scale remained open. How far out do those faint halo stars really go? How large is the dark matter envelope? Where does the galaxy's gravitational influence truly give way to the wider cosmic web? Before Webb, answers to these questions were based on indirect evidence and limited observations. Astronomers could track the motion of satellite galaxies and use that to estimate the mass and extent of the dark matter halo. They could search for faint stars in deep surveys, but those surveys covered only small patches of sky. The picture that emerged was something like a soft-edged sphere surrounding the bright disk, extending perhaps 200,000 or 300,000 light-years from the centre. Beyond that, the Milky Way's presence would blend into the gravitational fields of neighbouring galaxies, particularly Andromeda, which is on a slow collision course with us. This idea of overlapping halos hinted at a future where the two galaxies would merge, but it also suggested that the boundaries of each galaxy were already less distinct than a simple diagram might imply. So when people spoke of the Milky Way's size, they were often referring to the visible disk. The halo was acknowledged, but it lived in a somewhat abstract part of the conversation, something mentioned in passing rather than pictured in detail. All of this formed the background against which James Webb began its work. Astronomers were not expecting a complete overhaul. They were expecting refinement, better resolution, clearer images, more precise measurements. What they found instead was a quiet reminder that even the most familiar cosmic structures can still hold surprises, especially in the places where our previous tools couldn't quite reach. The Milky Way we thought we knew was not a mistake. It was a stepping stone, a version of the truth that fit the evidence available at the time, and like all good scientific models, it was designed to be replaced when better data came along. As Webb's observations started to fill in those faint, distant regions, the edges of the galaxy began to look less like a gentle fade and more like a complex, extended structure, with its own patterns and histories. The halo appeared richer, the outskirts more populated, the gravitational reach more pronounced. This doesn't mean that the galaxy suddenly grew overnight. It means our awareness of it did. At first glance, measuring a galaxy sounds like the kind of problem that should come with a very large ruler and a very patient scientist. You point, you measure, you write down a number, and you move on. But in practice, it's one of the most complicated tasks in astronomy, not because the math is especially tricky, but because of where we are standing while we try to do it. Imagine trying to map the size of a city while walking through its streets with a thick fog hanging in the air. You can see the buildings right around you. You can hear traffic in the distance. You might even catch glimpses of a skyline far away. But you never get the luxury of stepping back and seeing the whole thing at once. That's essentially the situation we're in with the Milky Way. We are residents, not visitors. We live inside the structure we're trying to measure. The most basic problem starts with distance. In everyday life, distance is intuitive. You walk from one place to another, you drive across town, you look at a map and get a sense of how far something is. In space, that intuition quickly falls apart. Even the nearest star beyond the Sun is more than 4 light years away. That's about 40 trillion kilometers. Numbers that large stop feeling like measurements and start feeling like abstract concepts. Astronomers have developed clever ways to measure distance, but each method works only within a certain range and comes with its own set of assumptions. The first and most direct technique is parallax. This is the same effect you notice if you hold your thumb up and look at it with one eye closed, then switch eyes. Your thumb seems to shift position against the background. That shift depends on how close your thumb is to your face. In astronomy, the idea is similar. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring that tiny shift and knowing the size of Earth's orbit, astronomers can calculate the star's distance using simple geometry. The problem is that this effect becomes incredibly small very quickly. Even for stars that are relatively close by in galactic terms, the shift is less than the width of a human hair seen from several kilometers away. Measuring it requires extremely precise instruments, and even then, parallax only works reliably for stars within a few thousand light years. That covers our local neighborhood, but the Milky Way is tens of thousands of light years across. For anything beyond the reach of parallax, astronomers have to switch to indirect methods. One of the most important of these involves something called standard candles. A standard candle is an object in space whose true brightness is known. If you know how bright something really is, and you measure how bright it appears to be from Earth, you can calculate how far away it must be. Light spreads out as it travels, so distant objects look dimmer. Certain types of stars are especially useful for this. Cepheid variable stars, for example, pulse in brightness in a regular pattern. The period of their pulsation is directly related to their true luminosity. Measure how fast they brighten and dim, and you can determine how much light they're actually putting out. Another kind of standard candle is a type Ia supernova, a specific type of stellar explosion that reaches a consistent peak brightness. These are so bright they can be seen in other galaxies, making them useful for measuring distances on a much larger scale. But inside the Milky Way, even standard candles have their limitations. Dust gets in the way. Cosmic dust absorbs and scatters light, making stars appear dimmer and sometimes redder than they really are. If you don't account for that correctly, you can underestimate how bright a star truly is and overestimate how far away it must be. And dust is not evenly distributed. It clumps into clouds, filaments, and thick bands, especially along the plane of the galaxy. That means some lines of sight are relatively clear, while others are heavily obscured. Two stars at the same distance can look very different depending on how much dust lies between them and us. So every distance measurement becomes a small puzzle. How much of the dimness is due to distance, and how much is due to dust? Astronomers build models of dust distribution to correct for this, but those models are based on observations that are, themselves, affected by dust. It's a bit like trying to map fog density while standing in the fog. Then there's the problem of crowding. The Milky Way is dense, especially toward the center. In some regions, there are so many stars packed into a small area of sky that they blur together. A telescope might see what looks like a single bright spot, but that light could actually be coming from dozens or hundreds of stars overlapping in the image. Separating those stars requires high resolution and careful data processing. Even with modern instruments, it's not always possible to disentangle every individual source, particularly in the most crowded regions of the galactic core. All of this makes it hard to create a clean, three-dimensional map. Instead of a crisp, clear picture, astronomers often work with layers of probability. This star is likely at this distance, within a certain margin of error. That cluster probably lies in this region of the arm, but it could be a little closer or farther than we think. When you scale that up to millions or billions of stars, the uncertainties start to shape the overall model of the galaxy's size and structure. Another layer of complexity comes from motion. Nothing in the Milky Way is standing still. Stars orbit the center of the galaxy. Gas clouds swirl and collapse. Satellite galaxies drift around us, sometimes passing close enough to disturb the disk. By measuring how stars move, astronomers can learn a lot about the galaxy's mass and shape. This is done through something called spectroscopy, which involves splitting a star's light into its component colors. The exact pattern of those colors can reveal how fast the star is moving toward or away from us, thanks to the Doppler effect. If a star is moving toward us, its light is shifted slightly toward the blue end of the spectrum. If it's moving away, the light is shifted toward the red. By measuring this shift, astronomers can calculate the star's radial velocity, its speed along our line of sight. Combine that with measurements of a star's position and proper motion, its movement across the sky, and you can build up a three-dimensional picture of its trajectory through space. This is incredibly powerful, but it's also data-heavy and sensitive to error. Small mistakes in velocity measurements can lead to big differences in inferred orbits, especially over long timescales. When astronomers look at the outer parts of the Milky Way, they often rely on the motion of stars and satellite galaxies to estimate how much mass lies inside their orbits. This is similar to how you can estimate the mass of the Earth by measuring the orbit of the Moon. The faster something is moving in orbit, the more mass there must be inside that orbit to hold it in place. So if a dwarf galaxy is zipping around the Milky Way at high speed far from the center, that suggests there's a lot of mass extending out to that distance, even if we can't see it. This method has been one of the main ways astronomers have estimated the size of the Milky Way's dark matter halo. But again, it depends on assumptions. You have to assume that the object you're measuring is in a stable orbit, and that you understand the forces acting on it. If a satellite galaxy is in the middle of being torn apart, or if it recently passed close to another massive object, its motion might not reflect the smooth, underlying gravitational field. So even gravity, which feels so reliable in everyday life, becomes a subtle and nuanced tool when you're dealing with structures that span hundreds of thousands of light years. There's also the issue of defining what size actually means for a galaxy. When we say the Milky Way is a certain number of light years across, what exactly are we measuring? Are we talking about the bright disk of stars, the faint halo of old stars, the invisible dark matter envelope, the region where the galaxy's gravity dominates over its neighbors? Each of these has a different boundary, and none of them have a sharp edge. The disk fades gradually. The halo thins out slowly. The dark matter extends far beyond the last visible star, blending into the dark matter halos of other galaxies. The gravitational influence of the Milky Way overlaps with that of Andromeda and other nearby systems. So any number you attach to the galaxy's size is to some extent a choice. It reflects a definition rather than an absolute physical wall in space. This is one reason why different sources sometimes give slightly different figures for the size and mass of the Milky Way. They may be measuring different components, or using different criteria for where the galaxy ends. Another complication comes from time itself. Because light takes time to travel, we never see the galaxy as it is right now. We see nearby stars as they were a few years ago. We see the center of the galaxy as it was 26,000 years ago. We see distant halo stars as they were hundreds of thousands of years ago. For most practical purposes, this doesn't matter. The galaxy doesn't change dramatically on those timescales. But when you're trying to build a precise model, it means that your map is always a collage of different moments in the past. It's a bit like trying to make a family portrait using photos taken over several decades. The overall shape of the family is there, but the details reflect different stages of life, different expressions, different moments frozen in time. Then there's the problem of background confusion. When you look out toward the edge of the Milky Way, you're not just seeing our galaxy, you're also seeing distant galaxies far beyond it. Some of the faint points of light in deep surveys are not stars in the Milky Way at all. They're entire galaxies, millions or billions of light years away. Distinguishing between a very distant galaxy and a very faint nearby star can be surprisingly difficult. Both can appear as small, dim smudges of light. Astronomers use color, motion, and spectral signatures to tell them apart, but those methods require high-quality data and careful analysis. Misidentifying background galaxies as halo stars or vice versa can skew estimates of how many stars the Milky Way has in its outer regions, and therefore how far it extends. All of this adds up to a situation where every measurement is part of a larger web of inference. Astronomers don't just measure one thing and declare the galaxy's size. They combine data from multiple sources across different wavelengths using different methods, and then build models that best fit all of that information. Those models are tested, revised, and sometimes replaced as new data comes in. This is where new instruments make such a difference. A telescope that can see in a new part of the spectrum, or with higher sensitivity, can break through some of the old limitations. It can reduce uncertainties, reveal hidden structures, and challenge assumptions that were built into earlier models. James Webb does exactly this by operating primarily in the infrared. Because infrared light can pass through dust more easily than visible light, Webb can see stars and structures that were previously obscured. It can peer into dense regions near the galactic center and into dusty areas of the disk and halo that older telescopes struggle to penetrate. It can also detect extremely faint sources, pushing the boundary of what counts as visible in the Milky Way. This makes it possible to identify stars in the far reaches of the halo and to study the distribution of faint low-mass stars that make up a large fraction of the galaxy's population. By combining Webb's data with information from missions like Gaia, which excels at measuring positions and motions, astronomers can create much more detailed three-dimensional maps. They can trace not just where stars are, but how they move and how they relate to the galaxy's overall structure. This is beginning to turn the Milky Way from a rough sketch into something closer to a living atlas, a dynamic model that shows not just static features, but flows, streams, and subtle patterns of motion. Still, even with these advances, the fundamental challenge remains. We are inside the system. We cannot step outside and take a single, clean photograph. We have to infer the whole from the parts, and those parts are always filtered through distance, dust, motion, and time. In a way, that makes the process more human. It's not about finding a final perfect answer. It's about gradually refining our understanding, filling in gaps, and being willing to adjust our picture as new information arrives. So when you hear that the Milky Way might be larger than we thought, what that really means is that our methods have improved enough to reach a little farther into the darkness. We're seeing stars that were always there, but were previously hidden or too faint to detect. We're tracing gravitational influences that were always shaping the galaxy, but were hard to map with older tools. The galaxy hasn't changed. Our view of it has. If measuring our own galaxy is this complex, this layered with uncertainty and interpretation, what does that say about how we understand our place within it, and how our own perspective shapes the cosmic stories we tell? Somewhere between the first time a human looked up at the night sky and the moment you settled into this very second, a quiet assumption has followed us along like a shadow. We tend to believe that what we see, or at least what we can eventually measure, is a fair representation of what is truly there. The world looks a certain size, the sky feels a certain distance away, and the universe, for all its mystery, seems like something that can be gradually boxed into diagrams, numbers, and tidy explanations. But when it comes to something as enormous as a galaxy, that assumption begins to soften at the edges. The Milky Way is not just large in the way a mountain is large, or an ocean is wide. It is large in a way that stretches the very idea of scale. It operates in units that have no natural place in everyday life. Light years, millions of stars, billions of years. These are not quantities we can directly experience. They are ideas we learn to handle through comparison, metaphor, and careful abstraction. And that is where human perspective quietly becomes part of the story. Our senses evolved to help us survive on a planet that is 8,000 miles across, orbiting a star that is one among many. We are very good at judging distances across a room, spotting movement in a field, or noticing subtle changes in light and sound. We're not naturally equipped to intuit the size of a structure that could swallow our entire solar system and never notice. So when astronomers talk about the scale of the Milky Way, they're not just dealing with instruments and data. They're also dealing with the challenge of translating something fundamentally inhuman in size into something the human mind can grasp. One way this shows up is in how we visualize the galaxy. Most people picture it as a flat spiral, like a glowing pinwheel floating in space. It's a useful image. It captures the idea of arms, a center, and a disk. But it also flattens something that is actually layered, thick, and three-dimensional into something that feels almost two-dimensional. The Milky Way's disk is not a thin sheet. It has depth. It has structure above and below the plane where most of the stars and gas reside. The halo extends far beyond that, wrapping the whole system in a faint spherical envelope. Dark matter stretches even farther, shaping the motions of everything within it. When we draw the galaxy on a page or a screen, we compress all of that into a symbol, and symbols, by their nature, leave things out. There's another subtler effect of perspective that comes from our position inside the galaxy. We are not neutral observers floating in empty space. We are embedded in a specific region, moving along a specific orbit, looking out through specific layers of stars, gas and dust. This means that the Milky Way does not present itself to us as a neat object with a clear outline. It presents itself as a sky full of points of light, streaked with a glowing band and punctuated by dark patches. Everything we know about the galaxy's shape and size has to be inferred from that internal view. Imagine trying to understand the shape of a city by standing on a single street corner and watching cars go by. You might notice that traffic flows in certain directions. You might see tall buildings in one area and shorter ones in another. Over time, you could build a mental map of where the downtown is, where the suburbs begin, and how the roads connect. But there would always be parts of the city you couldn't see directly. You would have to rely on second-hand information, indirect clues, and educated guesses. That's essentially how we study the Milky Way. We look at how stars move. We measure how light is absorbed and emitted. We trace the paths of gas clouds and satellite galaxies. From these pieces, we build a model of the whole, and just like any model, it reflects not only the thing being modeled, but also the perspective and limitations of the one doing the modeling. There's a psychological aspect to this as well. Humans are very good at thinking in relative terms. We understand big and small by comparing one thing to another. A house is big compared to a person. A mountain is big compared to a house. The Earth is big compared to a mountain. But when you get to the scale of a galaxy, those comparisons start to break down. The Earth is about 8 light minutes from the Sun. The Sun is about 4 light years from the nearest star. The Milky Way is about 100,000 light years across in its bright disk, and much larger when you include the halo. Each step up in that ladder of scale is not just an increase. It's a leap into a different category of size, and our intuition doesn't scale smoothly across those categories. This is why descriptions of the galaxy often rely on analogies. You might hear that if the solar system were the size of a coin, the Milky Way would be the size of a continent, or that if the Sun were a grain of sand, the nearest star would be miles away. These comparisons are helpful, but they are also reminders of how far removed the real numbers are from our everyday experience. Another limit of human perspective comes from time. We tend to think in years, decades, maybe centuries. History stretches back a few thousand years in our collective memory. But the Milky Way is billions of years old. It has been forming stars, absorbing smaller galaxies, and reshaping itself since long before the Earth existed. When we observe the galaxy, we are seeing it in a particular moment of its life. But that moment is just a thin slice of a much longer story. Even the light we see is a message from the past. When you look at a star in the night sky, you're not seeing it as it is right now. You're seeing it as it was when the light left it. For stars across the galaxy, that can mean tens of thousands of years ago. For distant galaxies, it can mean millions or billions of years ago. So the Milky Way, as we observe it, is a mosaic of different times layered on top of each other. Nearby stars are seen in the recent past. Distant halo stars are seen further back in time. The center of the galaxy, 26,000 light years away, is seen as it was when humans were just beginning to paint on cave walls. This time layering adds another level of complexity to our perspective. We are not just inside the galaxy, we are also looking back through its history piece by piece, without ever being able to see it all at once in a single, unified moment. There is also the matter of attention. Our instruments and our research programs are guided by what we choose to look for. For a long time, astronomers focused on the brightest, most active parts of the Milky Way. Star-forming regions, the galactic center, the main spiral arms. These areas are visually striking and scientifically rich. They tell us about how stars are born, how black holes behave, and how gas flows through the galaxy. But by focusing on them, we naturally paid less attention to the faint, quiet outskirts. The halo, with its sparse population of old stars and dim streams, did not stand out in the same way. It required deeper surveys, more sensitive instruments, and a willingness to spend time and resources on regions that, at first glance, seemed relatively uneventful. This is not a flaw. It's a reflection of how exploration often works. We're drawn to the places where things are happening, the fireworks, not the empty sky around them. But as tools like James Webb allow us to see fainter and farther, our attention can shift. And when it does, our picture of the galaxy begins to change, not because the galaxy itself has changed, but because we are finally noticing parts of it that were always there. Another subtle limit comes from language itself. The words we use to describe the galaxy carry assumptions. We talk about the edge of the Milky Way as if it were a solid object with a boundary. We talk about the shape of the galaxy as if it were something you could hold in your hands and turn around. In reality, a galaxy is a distribution of matter and energy. Its density varies gradually. Its influence fades rather than stops. Its form depends on what component you're talking about. Stars, gas, dust, and dark matter all have different distributions. So when we say the Milky Way is a certain size, we're really saying that one particular component of it, usually the bright disk of stars, reaches out to a certain distance. Other components go much farther. This layered nature doesn't fit neatly into simple descriptions. It requires more nuanced language, and nuance can be harder to communicate, especially outside of technical contexts. There's also a cultural dimension to perspective. For most of human history, the Milky Way was not a scientific object. It was a feature of the night sky, woven into myths, stories, and spiritual beliefs. It was a path for souls, a river of light, a bridge between worlds. When science began to describe it as a galaxy, a system of stars bound by gravity, that didn't erase those older meanings, it added another layer to them. Even today, when we talk about our place in the galaxy, there's often a quiet emotional undertone. We are a small part of something vast. We're not at the center. We're one star among hundreds of billions. This idea can feel humbling, comforting, or unsettling, depending on how you look at it. And those feelings can subtly shape how we engage with the science itself. There's a tendency, for example, to focus on the central regions of the galaxy, where the supermassive black hole resides, where star formation is intense, where things feel dramatic and important. The outskirts, by contrast, can seem like a quiet periphery, less interesting, less significant. But from another perspective, those outskirts are a record of the galaxy's history. They preserve the remains of ancient mergers and interactions. They hold some of the oldest stars, relics from the early days of the Milky Way's formation. So what seems peripheral from one point of view can be central from another. This shifting sense of what matters is another reflection of human perspective. We bring our own values, interests, and narratives to the way we study the universe. Even the technology we build reflects this. Telescopes are designed with specific goals in mind. Some are optimized for visible light, others for radio waves, others for infrared. Each one opens a window onto a different aspect of the galaxy. When a new window opens, like the one James Webb provides, it doesn't just add detail to an existing picture. It can change the picture itself by revealing features that were previously invisible. This is why the idea that the Milky Way might be larger than we thought is not just a technical update. It's a shift in perspective. It's a reminder that our mental image of the galaxy is shaped by what our tools allow us to see. There's a parallel here with everyday experience. Think about how a city feels different depending on how you explore it. If you only ever drive on the main roads, you get one impression. If you walk through side streets, parks, and neighborhoods, you get another. Neither view is wrong. They're just partial. In the same way, our view of the Milky Way has been shaped by the main roads of astronomical observation, the bright stars, the active regions, the easily detectable structures. As we start to wander into the fainter, quieter areas, our sense of the whole changes. There is also the matter of scale within scale. The Milky Way itself is just one part of a larger structure, the local group of galaxies, which includes Andromeda, Triangulum, and dozens of smaller systems. That group is part of a larger filament of galaxies, which is part of a vast cosmic web stretching across the observable universe. So even as we struggle to fully grasp the scale of our own galaxy, that galaxy is just a node in a much larger pattern. This can lead to a kind of nested perspective, where every time you think you've reached the edge of something, you discover that it sits inside something even bigger. From the surface of Earth, the sky feels vast. From the perspective of the solar system, Earth's orbit is a small loop around a single star. From the perspective of the Milky Way, the solar system is a tiny point in a disk of hundreds of billions of stars. From the perspective of the universe, the Milky Way is one among trillions of galaxies. At each level, what felt large becomes small. This doesn't mean our original perspective was wrong. It just means it was limited by the scale at which we were operating. In science, recognizing those limits is part of the process. Every measurement, every model, every theory comes with a range of validity. It works well within certain conditions and less well outside them. When astronomers revise their estimates of the Milky Way's size, they are not admitting failure. They're doing what science is designed to do, adjusting the model to better fit the evidence. There's something quietly reassuring about that. It suggests that our understanding is not fixed, it can grow, and that growth often begins at the edges, in the places where our perspective is weakest. The faint stars at the outskirts of the galaxy, the subtle motions of distant satellite galaxies, the barely detectable glow of ancient stellar populations. These are the places where our assumptions are most likely to be challenged, because they are the places we have seen least clearly. James Webb's role in this story is not just that it sees farther, it sees differently. By working in infrared, it bypasses some of the barriers that shaped our earlier perspective. It reduces the influence of dust. It highlights cooler, fainter objects. It brings parts of the galaxy into view that were previously hidden in shadow. As those parts become visible, the balance of the picture shifts. The bright, familiar structures are still there, but they are now set within a larger, more extended context. And that, in turn, feeds back into how we think about our own position. We're not just in a spiral arm of a galaxy. We're in a layered, evolving system with a long history and a wide reach. We are part of a structure that extends far beyond what we can see with our eyes, or even with most of our instruments. This doesn't change the fact that your room is still the size it was when you started listening. The Earth is still turning. The night sky still looks much the same as it did before James Webb launched. But it adds a quiet, expanded background to those familiar experiences. When you look up at the Milky Way band, you can think of it not just as a stripe of light, but as the dense midsection of a much larger, more subtle presence that surrounds you on all sides. And if our perspective has limits, that doesn't make it useless. It makes it a starting point. Every new observation, every new instrument, every new model is a way of stepping a little farther from that starting point, gaining a slightly wider view. Long before any images began quietly appearing on computer screens in control rooms and research offices around the world, the idea of a new kind of space telescope existed mostly as a problem to be solved. Astronomers knew what they wanted. They wanted to see farther into dusty regions, deeper into the early universe, and more clearly into places where visible light simply could not go. What they did not yet know was how many years of design, testing, revision and patience it would take to turn that desire into something that could actually unfold itself in the vacuum of space and begin to observe the cosmos. The James Webb Space Telescope did not arrive as a sudden invention. It grew slowly, shaped by decades of experience with earlier observatories and by the quiet realization that even our most successful instruments still left much of the universe hidden from view. To understand why Webb matters so much to the story of the Milky Way, it helps to step back for a moment and look at what came before it. The Hubble Space Telescope, launched in 1990, transformed astronomy. Its images of distant galaxies, nebulae, and star-forming regions reshaped how the public and scientists alike thought about the universe. Hubble worked primarily in visible and ultraviolet light, with some ability to observe in the near-infrared. From its position above Earth's atmosphere, it avoided the blurring effects of air and moisture, producing crisp, detailed views of space that were impossible from the ground. But Hubble also had limits. Visible light is easily blocked by dust. In the Milky Way, especially along the dense plane of the disk, thick clouds of cosmic dust obscure large portions of the galaxy. Hubble could see the glowing edges of these clouds and the stars around them, but much of what lay inside and behind them remained hidden. Astronomers could detect the presence of stars forming inside these dusty regions through radio and infrared observations from other instruments, but those views often lacked the resolution and sensitivity needed to study them in detail. This gap between what could be inferred and what could be directly observed became one of the driving motivations behind Webb. The basic idea was simple in concept and complex in execution. If dust blocks visible light but allows infrared light to pass through, then a telescope optimized for infrared should be able to peer into regions of space that were otherwise obscured. It should be able to see cooler objects, like forming stars, distant galaxies whose light has been stretched into longer wavelengths by the expansion of the universe, and faint stellar populations in the outer reaches of galaxies. So the vision for Webb was not just a bigger Hubble, it was a different kind of eye. Building that eye required solving a series of engineering challenges that, at times, bordered on the absurd. One of the first decisions was size. To collect faint infrared light, Webb needed a large mirror. The larger the mirror, the more light it can gather, and the finer the detail it can resolve. Engineers settled on a primary mirror 6.5 meters across, more than 2.5 times the diameter of Hubble's. But there was a problem. No rocket available could carry a solid mirror that large into space. The solution was to make the mirror out of segments that could fold up for launch, and then unfold and align themselves in space. Webb's primary mirror is made of 18 hexagonal segments, each coated in a thin layer of gold to improve their ability to reflect infrared light. Once deployed, these segments had to line up with extraordinary precision. If even one of them was slightly out of place, the telescope's images would be blurred. To achieve this, Webb was equipped with a system of tiny actuators that could adjust the position of each segment by fractions of the width of a human hair. Then there was the issue of temperature. Infrared telescopes are extremely sensitive to heat. If the telescope itself is warm, it will emit infrared radiation that can overwhelm the faint signals coming from distant objects. To work properly, Webb needed to be kept incredibly cold. Hubble orbits Earth, which means it passes in and out of sunlight every 90 minutes. That constant heating and cooling would be disastrous for an infrared observatory. So Webb was sent far away, nearly 1 million miles from Earth, to a location known as the Second Lagrange Point, or L2. This is a spot in space where the gravitational pull of Earth and the Sun combine in a way that allows a spacecraft to orbit the Sun in sync with Earth. From this position, Webb can keep its sunshield facing the Sun, Earth, and Moon at all times, blocking their heat and light. On the other side of the shield, the telescope sits in permanent shadow, cooling down to temperatures just a few degrees above absolute zero. The sunshield itself is a marvel. It's about the size of a tennis court and made of 5 layers of a special material designed to reflect and radiate heat. Each layer is separated by a small gap, allowing heat to dissipate gradually as it moves outward. By the time any warmth reaches the telescope side, it has been reduced to almost nothing. The deployment of the sunshield, along with the unfolding of the mirror and the extension of various booms and antennas, was one of the most complex sequences ever attempted in space. Hundreds of individual steps had to occur in the correct order, many of them relying on motors, cables, and hinges that had never been tested in the vacuum of space before. For weeks after launch, engineers and scientists watched telemetry data as each component moved into place. There was no way to send a repair crew if something went wrong. Webb had to succeed on its own. When the last mirror segment locked into position and the final alignment adjustments were made, the telescope began its scientific mission. What emerged from that effort was an observatory with capabilities unlike any before it. Webb carries several instruments, each designed to analyze infrared light in different ways. Some take images. Others break light into spectra, revealing the chemical composition, temperature, and motion of distant objects. Together, they allow astronomers to study everything from the atmospheres of exoplanets to the structure of galaxies at the edge of the observable universe. For the Milky Way, these instruments opened up a new way of seeing. Regions that had appeared as dark voids in visible light images began to show intricate structures in the infrared. Dense clouds of gas and dust, once seen only as silhouettes against glowing backgrounds, revealed networks of filaments, knots, and cavities carved by young stars. Star-forming regions that had been studied for decades suddenly looked different. Webb could detect the faint glow of protostars still wrapped in their natal cocoons. It could trace the distribution of molecules in the surrounding gas, offering clues about the chemistry that eventually leads to the formation of planets. But Webb's influence on our understanding of the Milky Way goes beyond these dramatic close-ups. One of its quieter strengths is sensitivity. Webb can detect extremely faint sources of infrared light, allowing it to see stars and stellar populations that were previously below the detection limits of other telescopes. This matters most in the outer regions of the galaxy. The halo of the Milky Way is populated by old, dim stars that emit much of their light in the infrared. These stars are spread thinly across vast distances, making them difficult to find and study. With Webb, astronomers can begin to pick out these faint points of light against the background of distant galaxies and cosmic infrared glow. By identifying and characterizing these halo stars, scientists can build a more complete picture of how far the Milky Way's stellar population extends. There is also the advantage of clarity. Infrared observations can cut through dust, reducing one of the biggest sources of uncertainty in distance measurements and star counts. This makes it easier to distinguish between stars that are truly part of the Milky Way and distant background galaxies that just happen to lie along the same line of sight. Webb does not work alone in this. Its data is often combined with information from other missions, especially Gaia, which measures the positions and motions of stars with incredible precision. Gaia tells astronomers where stars are and how they move. Webb helps reveal what those stars are like and where they sit in regions that Gaia struggles to see because of dust or faintness. Together, these two observatories create a kind of depth perception for the galaxy. Motion, position, brightness, and composition can all be considered at once, turning a flat star map into a three-dimensional dynamic model. This synergy has already begun to reveal structures in the Milky Way's outskirts that were difficult to confirm before. Streams of stars left behind by ancient mergers become easier to trace when their faint members can be detected more reliably. Subtle gradients in stellar populations across the halo can be studied, offering clues about when and where different parts of the galaxy formed. Even the distribution of dark matter can be inferred more accurately, because the motions of stars and satellite galaxies can be matched with a clearer picture of where visible matter actually resides. Another aspect of Webb's contribution is its ability to observe in multiple infrared wavelengths. Different materials and physical processes emit and absorb light at specific wavelengths. By looking at the same region in different parts of the infrared spectrum, astronomers can separate stars from gas, identify different molecules, and distinguish between warm and cool components. In the context of the Milky Way scale, this helps clarify what counts as part of the galaxy's structure. For example, some faint sources in the outer regions might be distant galaxies rather than nearby stars. Their infrared signatures can differ in subtle ways. Webb's spectral instruments can help make that distinction, reducing confusion and refining star counts in the halo. All of this adds up to a shift in how the Milky Way can be studied. Instead of relying primarily on visible light and radio observations, astronomers now have a powerful infrared window that fills in critical gaps. Regions that were once guesswork can be examined directly. Faint populations that were once statistical estimates can be observed individually. The result is not just more detail, but a change in confidence. When you can see something rather than infer it, you can test your models more rigorously. It's worth noting that Webb was not built specifically to measure the size of the Milky Way. Its primary science goals include studying the early universe, the formation of galaxies, the birth of stars, and the atmospheres of exoplanets. The insights it provides about our own galaxy are, in a sense, a bonus. But because the Milky Way is a galaxy like any other, the same tools that allow Webb to study distant systems can also be turned inward. In some ways, our galaxy becomes a nearby laboratory, where processes that shape galaxies everywhere can be observed in detail. When Webb looks at the outskirts of the Milky Way, it is not just measuring how far the galaxy extends. It is also studying how galaxies grow, how they interact with their environment, and how they assemble their mass over time. This connection between the local and the cosmic is part of what makes Webb's observations so powerful. The same faint stars in our halo that help define the Milky Way scale also tell a story about the history of the universe, because they formed in an era when galaxies were still coming together. The telescope's design reflects this dual purpose. Its large mirror and sensitive instruments are just as suited to detecting a tiny, cold exoplanet atmosphere as they are to picking out a faint star on the edge of our own galaxy. In both cases, the challenge is the same: find a small, subtle signal in a vast, complex background. From a more human perspective, there's something quietly remarkable about the way Webb operates. It does not take pictures in the way a camera does. It collects photons, tiny packets of energy that have traveled for years, centuries, or millennia before reaching its mirror. Those photons are then turned into electronic signals, processed into data, and eventually translated into images and graphs that we can interpret. By the time you see a Webb image on a screen, it has passed through layers of technology and human understanding. It is not a raw view of reality. It is a carefully constructed representation, shaped by the design of the instrument and the choices of the scientists who analyze the data. This doesn't make the images less real. It makes them part of a conversation between the universe and the people studying it. In the case of the Milky Way scale, that conversation is still ongoing. Webb has begun to contribute new lines of evidence, but those findings are being tested, debated, and refined. Some studies suggest that the stellar halo is more extended and structured than previously thought. Others focus on specific regions, mapping out how far certain populations of stars can be traced. Still others use Webb's data to improve models of dust distribution, which in turn affects distance measurements across the galaxy. Each of these efforts adds another piece to the puzzle. What's notable is not that Webb has delivered a single definitive answer, but that it has expanded the range of questions that can be asked. Instead of simply asking, how big is the Milky Way, astronomers can now ask, how does its size vary depending on which component we look at? How did its outer regions form? And how does its structure compare to that of similar galaxies in different environments? These are more nuanced questions, and they reflect a deeper level of understanding. As Webb continues to operate, its role in this story will likely grow. More surveys of the galactic plane and halo are planned. More detailed studies of star streams and satellite galaxies will be carried out. Each new data set will be another opportunity to test and refine our picture of the galaxy. From the outside, this process can look slow. Discoveries are announced, then revised, then discussed again. But from the inside, it's a steady, careful expansion of knowledge, guided by evidence rather than expectation. In a way, Webb itself embodies the theme of scale. It is a human-made object, built on Earth, launched by a rocket, and operated by people sitting at desks and looking at screens. And yet, it reaches out across millions and billions of kilometers, gathering light from stars and galaxies that formed long before any of those people were born. When it turns its attention back toward our own galaxy, it becomes a tool for self-exploration on a cosmic level. It allows us to see our home from a new angle, not by stepping outside it, but by peering through the layers that once blocked our view. As those layers become more transparent, the Milky Way begins to look less like a neat, bounded object, and more like a sprawling, evolving system with a long, complex history. That shift in view does not happen all at once. It unfolds over time, observation by observation, analysis by analysis. Beneath the bright band of the Milky Way that stretches across the night sky, there lies another version of our galaxy that most human eyes will never see. It is not made of glowing stars and obvious shapes, but of shadowed regions, cold clouds, and fine grains of material drifting quietly between points of light. This hidden layer does not announce itself. It does not shine. It absorbs, scatters, and softens what passes through it, shaping our view of the galaxy in ways that are easy to overlook and hard to fully account for. Cosmic dust is one of the great organizers and one of the great obscurers of the Milky Way. The word dust might suggest something small and insignificant, but in space this material plays a central role in how galaxies look and how they evolve. It is made of tiny, solid particles, often smaller than a grain of smoke, composed of carbon, silicates, ice and trace metals. These particles form in the atmospheres of dying stars and in the debris of stellar explosions, then drift outward into the space between stars, where they become part of the raw material for future generations of suns and planets. Invisible light, dust, is a troublemaker. It blocks starlight. It dims distant objects. It creates dark lanes and patches that cut through otherwise bright regions of the galaxy. Some of the most striking images of the Milky Way show these inky shapes snaking across glowing starfields, like silhouettes of something solid against a luminous background. From a scientific point of view, those silhouettes are both a clue and a barrier. They tell us where dense clouds of material are located, but they also prevent us from seeing what lies behind them. For decades, large portions of the galaxy, especially toward the central regions, were effectively hidden from optical telescopes. Astronomers knew that something was there, but they could only guess at the details. To understand how profound this effect is, It helps to think about how light behaves when it encounters dust. Visible light has relatively short wavelengths. When it strikes a dust particle, it can be absorbed or scattered in different directions. Over long distances, this process can remove a large fraction of the light from a beam travelling toward Earth. The farther that light travels through dusty regions, the dimmer and redder it becomes, because shorter, bluer wavelengths are scattered more efficiently than longer, redder ones. This effect, called interstellar reddening, is one of the main reasons distant stars often appear redder than they truly are. It also means that some stars become so dim in visible light that they effectively disappear from view, even though they are still there. Infrared light behaves differently. Its longer wavelengths allow it to slip past many of the dust particles that block visible light. It is not completely immune to absorption, but it is far less affected. This makes infrared astronomy a powerful tool for exploring the hidden parts of the galaxy. When James Webb was designed, this property of infrared light was one of its main advantages. It was built to look through the dusty veil that has shaped our view of the Milky Way for generations. Before Webb, astronomers relied on a patchwork of infrared observations from ground-based telescopes and earlier space missions. These provided important insights, but they were limited in resolution and sensitivity. They could show large-scale structures, but not always the fine detail needed to understand how those structures fit together. Webb changed that balance. With its large mirror and highly sensitive instruments, it can collect faint infrared light from distant and obscured regions, resolving individual stars and structures that were previously blurred or invisible. This capability opens up a different way of seeing the galaxy, one that is less dominated by the brightest, least obscured regions and more inclusive of the quieter, hidden ones. One of the most dramatic examples of this comes from star-forming regions. In visible light, many of these areas look like dark, irregular clouds. They appear as holes in the star field, places where something seems to be missing. In reality, those clouds are packed with gas and dust, and inside them, new stars are being born. As a star begins to form, it gathers material from its surroundings, growing hotter and denser. At first, it is completely wrapped in a thick cocoon of dust and gas that blocks almost all visible light. Only when it becomes hot and energetic enough to blow away or heat up that surrounding material does it begin to shine in the optical range. Infrared light can escape much earlier. With Webb, astronomers can see into these cocoons and observe stars at very early stages of their development. They can trace the shapes of the clouds, the filaments of material feeding the growing stars, and the cavities carved out by stellar winds and radiation. These observations are not just visually striking. They help scientists understand how efficiently stars form in different parts of the galaxy, how mass is distributed, and how energy flows through the interstellar medium. And this, in turn, relates back to the scale of the Milky Way. A galaxy's size is not just a matter of how far its stars extend, it is also about how its material is organized and how it cycles through different phases. Gas and dust are constantly being transformed into stars, and stars, when they die, return material back to the interstellar medium. This cycle happens across the entire galaxy, from the crowded central regions to the faint outskirts. By seeing through the dust, Webb allows astronomers to study this process in places that were previously difficult to access, giving a more complete picture of how the Milky Way sustains itself across its full extent. Another important aspect of dust is that it is not evenly distributed. In the Milky Way's disk, dust tends to concentrate along the spiral arms, where gas is denser and star formation is more active. This creates long, dark lanes that trace the structure of the arms themselves. In visible light images of other spiral galaxies, these dust lanes are often seen as thin, dark lines winding around the bright cores. Because we are inside the Milky Way, we see these lanes from the side rather than from above. They show up as broad, irregular bands and patches that can stretch across large portions of the sky. This uneven distribution of dust creates a kind of observational bias. Regions of the galaxy that happen to lie behind thick dust clouds are underrepresented in visible light surveys. Regions with clearer lines of sight are overrepresented. If you try to count stars or map structures using only visible light, you will naturally get a picture that is shaped by where the dust happens to be. Infrared observations help correct this bias. By comparing how a region looks in visible and infrared light, astronomers can estimate how much dust lies along that line of sight. This allows them to adjust the apparent brightness of stars and get a better sense of their true luminosity and distance. Over large areas of the galaxy, these corrections can make a significant difference in star counts and distance estimates. That in turn affects how far the disk and halo appear to extend. In some cases, regions that once seemed sparsely populated turn out to be rich in stars that were simply hidden behind dust. This has particular importance near the galactic center. The core of the Milky Way is one of the most crowded and dust-obscured regions in the sky. In visible light, it is largely invisible. Thick clouds of dust block our view, leaving only a few bright stars and glowing patches to hint at what lies beyond. Infrared telescopes have gradually peeled back this curtain over the years, revealing a dense cluster of stars and the presence of a supermassive black hole at the center. Webb adds another layer of clarity to this picture. It can resolve stars in the central region with greater detail, study the distribution of gas and dust around the black hole, and trace how material moves and interacts in this extreme environment. While this may seem far removed from the question of the galaxy's overall size, it is part of the same story. The center of the Milky Way is a key anchor point for models of the galaxy's structure. Knowing its mass, motion, and distribution of stars helps define the orbits of everything else. Better data about the center leads to better models of the disk and halo, and ultimately, better estimates of how far the galaxy's influence extends. Dust also plays a role in how we distinguish between stars in the Milky Way and distant background galaxies. When looking toward the outskirts of the galaxy, especially at high galactic latitudes, astronomers often encounter faint, small sources of light. Some of these are dim stars in the halo. Others are entire galaxies far beyond the Milky Way. In visible light, these can look very similar. Both appear as tiny, blurry points. Infrared observations can help tell them apart. Distant galaxies often have different infrared signatures than nearby stars. Their light has been stretched by the expansion of the universe, shifting it into longer wavelengths. They may also show the combined glow of billions of stars and warm dust within the galaxy itself. By analyzing the infrared spectrum of a faint source, astronomers can determine whether it is likely a halo star or a distant galaxy. This reduces confusion and makes star counts in the outer regions of the Milky Way more reliable. And those star counts are a crucial ingredient in determining how far the galaxy extends. Another layer of darkness that Webb helps address is not caused by dust at all, but by temperature. Many objects in space are simply too cool to emit much visible light. Low-mass stars, brown dwarfs, and certain types of stellar remnants shine primarily in the infrared. These objects can be numerous, especially in older populations like the galactic halo. Because they are faint and cool, they are easy to miss in optical surveys, but they still contribute to the galaxy's mass and structure. By detecting these cooler objects, Webb helps fill in another part of the picture, revealing a population of stars that were always there but often overlooked. This matters when astronomers try to estimate the total number of stars in the Milky Way and the distribution of mass across the galaxy. If a significant fraction of stars are faint and cool, then visible light surveys alone will underestimate their presence, especially in distant or obscured regions. As more of these objects are detected, the apparent size and richness of the galaxy's stellar population can increase. Darkness, in another sense, also refers to the vast stretches of space between stars. The Milky Way is not a solid mass of light. It is mostly empty. Even in the dense regions of the disk, the average distance between stars is several light-years. In the halo, those distances grow much larger. This emptiness can make the outskirts of the galaxy difficult to define. When stars become very sparse, it becomes harder to tell where the galaxy ends and intergalactic space begins. Infrared sensitivity helps here as well, by allowing astronomers to detect stars that are both faint and isolated. A single star in the far halo might emit so little light that it blends into the background noise in visible light images. In the infrared, it can stand out just enough to be identified and studied. Each such detection extends the known reach of the galaxy by a small amount. Over many observations, these small extensions can add up to a significant revision of the galaxy's scale. There is also the role of dust in shaping how we think about structure. Because dust tends to trace spiral arms and star-forming regions, our mental image of the Milky Way shape has been influenced by where the dust appears. Dark lanes in visible images often mark the locations of arms. Bright regions highlight areas of active star formation. When infrared observations reveal stars behind those lanes, it can change how those structures are interpreted. What once looked like a gap between arms might turn out to be a region filled with stars that were simply hidden from view. This can lead to adjustments in how the number and shape of spiral arms are modelled, which in turn affects the perceived size and geometry of the disk. Another interesting aspect of dust is its temperature. Dust grains absorb energy from nearby stars and re-emit it in the infrared. By measuring this emission, astronomers can estimate the temperature and density of dust clouds. Webb's instruments can map these properties across different regions of the galaxy, revealing variations that hint at different environments and histories. In the outer parts of the galaxy where star formation is less active, dust tends to be cooler and more diffuse. Detecting this faint emission can be challenging, but it provides information about how far the galaxy's interstellar medium extends. If dust and gas are found far from the bright disk, it suggests that the galaxy's material envelope reaches farther into space than previously thought. This, again, feeds back into the question of scale. There is also the interplay between dust and dark matter. While dust itself does not interact directly with dark matter, both are influenced by the galaxy's gravitational potential. The distribution of dust and gas can trace the underlying shape of the dark matter halo in subtle ways, especially in how material flows and settles over time. By mapping dust and gas in the outskirts of the galaxy, astronomers can test models of the halo's shape and extent. Webb's ability to detect faint dust emission and obscured stars provides new data for these tests, helping refine our understanding of the invisible structure that holds the galaxy together. From a more human standpoint, there is something quietly poetic about the idea that much of the Milky Way's true form has been hidden behind a veil of dust, waiting for a different kind of light to reveal it. For centuries, people looked up at the night sky and saw a glowing band, a river of stars. That view was shaped by the dust that both blocked and highlighted different parts of the galaxy. Now, with infrared eyes, we are beginning to see beyond that surface, into the deeper layers that were always there but out of reach. This does not replace the old view, it adds to it. The visible Milky Way is still real,